Welcome to AI for Decision Makers. My name is Rob Zucker. In this video, by way of a simple example, I will make a high-level comparison between traditional and machine learning, or ML to shorten it to its usual term, approaches to providing a solution. Well, let's define the problem. To calculate the stopping distance given an entry speed and rate of deceleration. We'll be using the metric system, and we will be making a key assumption. The rate of deceleration remains constant. Now, when we're comparing the two approaches, this provides quite a useful insight into how ML and traditional approaches can differ. And here is the data. So these are actual measurements, if you like. These two columns provide the input data, and this the result. Here we are actually displaying a subset of all the data, as we have 95 rows of data that were created. Let's have a quick look at how we would apply the traditional approach. First of all, we would begin with the input data. We would then apply a set of predefined rules, e.g. a program, which will generate the output. So this seems pretty straightforward. Now let's have a look at how we would apply it to the data we saw a moment ago. Here's the subset of data again. As you can see, the speed and deceleration are the input data. There's a rule, which is this rule, which defines how we're going to create the output of the outcome. I'm not going to go into the mathematical formula, but just to point out it is a predefined rule. And then we have the stopping distance calculated here. So far, so straightforward. But what happens if it isn't that straightforward? For example, what if the braking rate is not constant and varies, for example, by approach speed? That could then require a much more complex formula in order to calculate the stopping distance. So please bear that in mind. And now let's have a look at the machine learning approach. How does the ML approach differ? This diagram shows the three components of the ML approach. In the center, we have the ML model, which we'll be discussing later. And then the two key inputs. On the one hand, we have the speed and deceleration, which is similar to the traditional approach, but we also include the known stopping distances. So how does the model actually work? In a nutshell, what happens is, based on its current settings, the ML model creates a forecast of the stopping distance. It then compares this with the actual stopping distance, and based on the difference, updates its internal settings. The objective the model has is to narrow the gap, or if you like, the error between the actual and the forecast stopping distances. And it iterates or repeats the process until the error is sufficiently low. One key difference between the ML and traditional approaches is that the former does not require the underpinning assumption we had earlier. Now we'll have a look at the steps that we will go through to create a machine learning solution. Firstly, we'll retrieve the data. You've seen some of this already. We have 95 rows. It's worth mentioning that in the real world, the preparation of a good set of data is one of the most demanding tasks in preparing a solution. Very often the data has missing values and outliers that need to be dealt with. We then create the ML model. We feed this data into the model. We'll run this for about 200 iterations, or epochs to give it its correct term. The idea is that with each iteration, we close the gap between forecast and actual outcomes, i.e. we reduce the error. This is a diagram of the machine learning model that is being used. To use the jargon, it is a dense neural network. Neural because it has a parallel with how the brain processes information. For example, each of these numbered ovals behaves like a neuron. Network because there are connections between the layers, which you'll see in a moment. And dense because there is a connection between each neuron in a layer and its adjacent layer. So for example, this one here, one connects to that one, and all the way down to the 64th neuron or function. So how does it work? Well, let's have a look at the input data deceleration. The deceleration data is fed into each of the layer 1 functions / neurons. So it looks a bit like this. So the deceleration information is fed into all 32 neurons. Now, apart from the data itself, each data carries something called a weight, and that weight can be modified by the machine learning model. Similar to these links, there are loads of other connections. This is just a sample. Now remember, I said earlier that a dense neural network, as this represents, has connections between the layers. This, for example, 1 connecting to all of the functions such neurons that are in 2. Similarly, 2 connects to all of them. So just doing a bit of straightforward maths, you'll see that the number of available connections is approximately 32 by 64, which is over 2000. What a machine learning model does is it updates the weights that each of the connection carries in order to move its forecast outcome as close as possible to the actual outcome for known data. And it does this on a number of occasions. The number of occasions set by the number of epochs or iterations. So we have up to around 2000 connections, and we'll be iterating or updating these up to 200 times. So as you can see, there's a lot of fine-tuning that can take place. The ML model and data discussed in the previous slides has been translated into an ML solution. For those interested in the technical aspects, I use Microsoft Excel to generate the data, randomly generating the input speed. I use Google's TensorFlow to create the machine learning model, and I use the Python language to bring it all together. As the ML model was run, the error in the model's predictions was captured. And in the graph on the right-hand side, you can see how accuracy improved after each epoch. How did we do? Well, as you can see from the training loss, the blue line, it drops to less than a 2-meter error after 200 iterations. Is that acceptable? Well, it really depends on requirements. Interestingly, the amber line drops to a 1-meter loss. So it is actually performing better than the training would suggest. Let's look at some of the advantages and disadvantages of machine learning. On the advantages side, and a couple of examples of the advantages are potentially identifying new profitable marketing segments and the use of machine learning on the healthcare side to follow up with COVID vaccinations and checking on side effects. On the disadvantages side, now that is essentially what we're covering today. So let's just have a look at a summary of what we've gleaned. To summarize, even though we've provided a simple example, we've managed to demonstrate that a machine learning approach learns from data without requiring the underlying business rules. Machine learning and traditional approaches both have their strengths and weaknesses, and we've listed some of the advantages and disadvantages of the machine learning approach. That's it for this set of slides. Just like to let you know that soon we will be releasing an article entitled Developing a Business Case for AI. But if you found this video useful, please click on like and subscribe below. Many thanks, and we'll speak to you soon.